Okay. There are two naming conventions. One's called ionic and the other's called molecular or covalent. So you need to first figure out what kind of compound you're working with. Is it ionic, covalent? Now, I usually say covalent rather than molecular. Did anyone not get the two handouts? Okay. They'll be up here. So before you leave, make sure you grab them. Okay. So what I've given you, one of the handouts, I've given you two handouts. One handout was on common ions. You do not have to memorize that. However, some of the 1A and 2A teachers require you to memorize part of this. So just FYI. You're going to have this during your tests, this common ion chart. Okay, so what you need is a common ion chart to figure out whether your compound is ionic or not. If it's not ionic, then it's covalent. Unfortunately, the naming conventions are different. That's why you have to figure out what you got first. Okay. Yes, covalent and molecular are the same thing. All right. Ions, as you remember, are either positive or negative. On the left are the positives, the cations. On the right are the negatives, the anions. And notice on the top right, I've got something called covalent here. So when you're using the covalent naming convention, you need to know these mono, di, tri, tetra, penta, hexa, etc. For the covalent or the molecular, you don't use those, only the covalent. So, and most students find the covalent naming easier than the ionic. So I'm going to cover the molecular or covalent one first. All right, so if I put down something like this, okay, that's a binary compound. It's got two things in it. Is that ionic or covalent? Okay, this is how you find out. Okay, if it's ionic, yes. Yes. Yeah. Okay, now remember the metalloids on your periodic table, the squiggly black line up there. Everything to the left of that are metals. Everything to the right of it are nonmetals. So an ionic compound's got to have something on the left, something on the right of the squiggly metalloid line. So is sodium chloride ionic or molecular? Okay. Well, where's sodium located? Left or right? Left. And then chloride is on the right. Okay. So that is ionic then. Another way to tell is to look on your common ion chart. We have sodium down here. Right there. And we have chloride up here. So another way to tell ionic is there a cation and an anion there? Yes. So that's the first step. Is it ionic or molecular? If it's not ionic, then it's molecular. So you first check to see if it's ionic or not. Let's look at another example. Okay, how's this? Is this ionic or molecular? Okay, it's two nonmetals. Two nonmetals. Nitrite is N minus 3 right here. And then oxygen is oxide right here. So that's molecular. Okay. Or it's got two anions together. Doesn't work. Okay. So how do you name these things? Next step. Both ionic and molecular always have two parts. So let's name this N2O3. So what does N stand for? Nitrogen. That's directly from your periodic table. The second one is O, that's an ide from your common ion chart. So that's oxide. Yeah. Say again? It's just the convention. So the second one is always an ide. And you can get it off your common ion chart. Okay, now the next step, well, the first step is ion or covalent. Second part is put the names down. Third step is how many of each do you have? Okay, we've got two nitrogens. So that's di. And that's from the top part of your common ion chart. And we have three oxygens. So it's dinitrogen trioxide.
Except if it's the first one, you skip it if it's mono.
Okay, so its question had to do with one. What if we just had let's name that NO. We already know it's molecular. So we have same thing, nitrogen oxide, and we have one of each. Now the one over here is required. The one in the beginning is optional. Now, one of the things that frequently is done is you have two O's together there. They'll frequently merge those together. Into monoxide. So the mono in the beginning is optional. If you want to put it there, put it there. That way it's consistent. But frequently they leave it off. It's in the beginning. So if there's nothing there, it's mono. Okay, pretty straightforward. Covalent. Now, the next thing is to take a name and generate a formula from it. Kind of going the opposite way. And by the way, ionic does not have any of this mono, di, tri stuff in it. So if you see that in a name, it's automatically molecular or covalent, automatic. So let's do so monohydride, mononitride. How do we generate a formula from that? Okay, first of all, penta is what? How much? 5. Mono is 1. So we have 5 of the hydrides. Hydride is hydrogen. Nitride is nitrogen. Excuse me. Hydride is hydrogen. Nitride is nitrogen. So that's the formula for pentahydride nitride. Yeah, probably should do that. Let's make this pentahydrogen mononitride. Yeah, the I's are always on the second one. I was just not looking at the right thing. There's an ongoing battle at my apartment complex, and they're dragging me into it. Life was so much simpler when I lived in a single family home. All right, let's try another one. Okay, trichlorine heptaoxide. Tri is how many? And hepta is how many? 7. So that would be, that's a 7, believe it or not. Okay, so that's molecular. Now, the reason why we have to put tri and mono and all that stuff in it is because there's no way to tell how many of each you should have. And I mentioned earlier that with ionic, you don't have to put those in. And the reason with ionic, you don't have to put it in because you have charges on the ions that you have to balance. And that automatically dictates how many of each you have. So are there any questions about molecular? Most students think that's easier than the ionic.
Now,
Well, the charge balancing forces numbers. You'll see in a second here what I'm talking about. All right, so let's go ahead and look at ionic now. Ionic is also in two parts. There's a positive cation and a negative anion. Okay, so let's look at calcium hydroxide. Okay, remember now the first one is positive. So calcium, if you look on your common ion chart, calcium's towards the top, it's going to be a +2. And hydroxide on the bottom is -1. So what's the net charge the way I wrote those?
Like,
Yeah, it's not 0, is it? Okay, the net charge has to be 0. So how many -1s do we need to balance that +2? One more, right? We need -2, +2. Okay, hydroxide by itself is a -1 charge. So that's why we need 2 of the hydroxides. So calcium hydroxide is going to be Ca, and we know the charge in the Ca is +2. We need 2 hydroxides. So with ionic compounds, the net charge has to be 0. Now this is why we don't have to say dihydroxide, because hydroxide is -1, has to balance the +2 of the calcium.
why is it bracketed?
Okay, the question is, why is it bracketed? Because the OH is a group, and OH by itself is -1 together. So to say 2 of them, you have to put parentheses around it. Otherwise, it would only apply to the H. Now, sometimes the elements that are in the middle have multiple ions versions. So if you look on the left, we go down to nickel, for example. Nickel exists in about 5 different versions. I have 2 of them on here, the +2 and the +3. Now notice so if I just said nickel, you wouldn't know which nickel. So what they do is they put in parentheses the Roman numeral that corresponds to the charge. Now you have to know your Roman numerals. You only need to know 1, 2, 3, 4, which is IV, and 5V. So if there are multiple versions of the cation, and they all are from the middle area, you'll see them marked like this in parentheses. Now, if you were to take and look at a food label, and in your food label is copper sulfate, for example, they're not going to say copper 3 sulfate. You're going to say cupric sulfate. And whenever there are two versions, two names, I've listed them here. So cupric is the same as copper 2. Now the department does not teach those names, the cuprics, the cupresses, and all that stuff. I personally do, because when you look at a food label, that's what they use. They don't use, when you go to an analytical store that sells chemicals to schools and to companies, they use the parentheses. But when you go to the store to buy something, or you go to a feed store to buy something, fertilizer or something, they use the old naming system. So you need to be exposed to both. That's why I teach both. So, okay, does that make sense? So the parentheses says, I like the parentheses because it's very clear what the charge is. The problem with naming it the old-fashioned way, you don't know what the charge is. All you know is there's an ick and an us. The ick is a higher charge than the us, but that's it. It's all you know. You don't know if it's a +2, +3, +5, whatever. You don't know what it is. Where with the newer system, I mean, I'm saying new, it's been out for like 90 years, but you know exactly what it is in parentheses. So just be aware sometimes there are two names for something, and that only applies for the ones in the middle there, the elements in the middle, because they form multiple ions. Okay. All right. Let's look at aluminum sulfate. Okay, so what's the charge on aluminum? +3. What's the charge on sulfate? On the right, in the middle, -2. Okay. What's the net charge if you have one aluminum and one sulfate? +1, so it's not 0. How do we make it 0? 2 and 3. We had 2 aluminums. What does that come to? Well, each one is +3. So what is 2 aluminums? What's the charge on 2 aluminums? 2 3s. Huh? 6, right. Okay. And how many -2s do we need to get up to 6? 3. So that's the formula for aluminum sulfate. Okay, so that's going from name to formula. Let's do some formulas to names. Oh, let's see. Okay, so let's do one more name to formula. There's a problem with that name. What is wrong with the way I wrote that? Right, we don't know what the, yeah. Yeah, we don't know what the charge is in vanadium. Notice vanadium, I have 3 of them there. Which one is it? Well, we don't know. So let's go over to the oxide, because the way it's written, the net charge is 0. So what's the charge on oxide? -2. And what does that do to the vanadium? Which one do we use? Which one? We need it to be +2, yeah. So it's vanadium oxide. And this vanadium should have been written like this to indicate, but it doesn't need to be written because we know there's only one oxide and oxide's -2. So sometimes in your dry lab, they're going to do stuff like this. So just remember, it has to be a net charge of 0.
Sorry, you said you don't need right two because in the common iron chart, this does vanadium, it shows that
There are 3 of them. And oxide over here is -2. So if you have 1 and 1, this forces that to be the 2 version.
but wouldn't you still write it because it's a variable charge panel?
To be more correct, yeah, I should have put it in there. I was just making a point though, that one forces the other.
Right, yeah.
Okay, oh, let's see here. Okay, so let's name this iron phosphate. Well, first of all, again, iron exists in multiple forms. So we don't know yet which one. So let's look at the phosphate. Phosphate only exists in one form, and it's a -3. So what does that force the iron to be? Iron 3. Notice no tries, no dies, none of that stuff. Ah, you mean on the POH? Repeat your question again. Yeah, because there's multiple forms of iron. So we have to distinguish which one. Yep. Ah, okay. So her question is, why don't we do that? Ah, okay. So parentheses means you're talking about the whole group. P, 1P, 4 O's. They're a group together. Can't split them up. So that's what the parentheses indicates, that it's a group. Now, if there's only one of them, you don't put parentheses there. But if there's more than one, If you have to put the parentheses there. Okay. So if on the right side of your common ion chart, there's a lot of anions that have multiple atoms in them, like SO3, SO4, CO3, CO2. I mean, there's a whole bunch of them. And anytime there's more than one of those, parentheses. But if it's just one, it's optional. And if you can put it in there. You can put the parentheses there with a one, that's fine too. So if you want to just be consistent, you can always do that. It's like mono in the beginning, one of those optional things. That was a good question though. Okay, so I'm trying to think of all the examples we're going to run into. If you look on your ion chart, why did it go away? We look at acetate here. Notice there are two ways to write that. Both of them are correct. It's just one is an inorganic way and the other is an organic way. The top one is the preferred one. That's the way you'll usually see acetate written. And it comes from its companion acid, acetic acid. The bottom one is frequently written, if you're an inorganic chemist, that's the way they write it. Same with formate. Organic, inorganic. Doesn't matter which one in this class you do. In your textbook, you'll probably see the top versions rather than the bottom versions. Okay, so that's naming ionic molecular compounds. And you just need a lot of practice. Now I have now Dry Lab 5 practices it a lot. The naming. In addition to that, they don't give you the answers though. If you want practice with answers, I have worksheets for you over here. So we go down to naming covalent compounds, naming ionic and covalent compounds. So I've got 3 worksheets there for practice, and they have the answers in it as well. So if we were to pull up now, naming. First step is it ionic or covalent or molecular? Step number 1. Step number 2. Then you need to go into the different conventions. Remember with covalent and molecular, you have to use the mono-di tripart. With ionic, you have to balance the charges. Charges need to be net 0. So here I want you to write formulas. Well, notice right away, well, you can't see it, with the brackets around the first one there, copper 2 acetate, you know, right away it's ionic because it's got brackets in there. Boom. Ionic. If it's got that's just the name of the anion. Is towards the bottom. That was the one I,
Oh, and it's organic acids. It's acid.
okay. So again, all these ones with brackets are ionic. Most of these are ionic, actually. And I give you the answers. Yeah, because only the metals have multiple charges. And, yeah, that means you automatically have to bracket it. So boom, that means it's automatically a cation.
It's not hard to practice, just show it for class. It's like
Starting 1 + 2 + 3. And then it starts from the opposite end at -1, -2, -3.
for
Remember in the group, every group has got the same chemical characteristics.
Right.
Because its valence setup is the same. So if one does a +2 charge, they all do. Because their valence is set up the same. So starting over here, you go +1, +2, you skip the middle because they're all over the place. And then you pick it up, pick it up here at +3. And then the group from carbon does neither a plus or minus. It doesn't form ions. And then starting on with nitrogen group, that's -3, -2, -1, 0. So carbon is kind of in the middle and it goes out from there. 3, 2, 1, 0. The what? Yeah, the 3 in the end form anions. Those are the non-metals, basically. Let me pull up a periodic table. I gotta. Okay, let's talk about the periodic table a tiny bit. What he was referring to is within the group, like group 1, for example, the alkali metals, they all form a +1 charge. The alkali earth metals, +2. And we skip the middle part here, because those form different charges all over the place. We go over here starting with boron, they all do +3. Carbon group doesn't form a charge. The nitrogen group is -3. Oxygen group, -2. Excuse me, the halogens, -1. And the noble gases are 0. So it goes +1, +2, +3, 0. Because carbon will be a +4 or a -4. So it does neither. And then backs down from carbon, goes to nitrogen -3, oxygen's -2, the halogens are -1, and the noble gases are 0. So they're very systematic.
Chart is different from valence electron.
I'm sorry?
The chart is different than valence electron.
Yeah, yeah. It has to do with how stable the electron configuration is. Tomorrow I was going to talk about that. Keep that question in your mind. Okay, that's what I wanted to cover today. What I'd like you to do now is to practice some of this naming. You can either do it by pulling out your lab packet and starting on naming for Dry Lab 5. Or you can go home. I'm sorry, on what? Would I modify it? Oh, zoom out. Far enough? Now there's a video all about the periodic table.